So now that we've looked at what waves are and the different parts of them, we need to look at how they behave. So the three main terms we are going to have in this topic are that waves can reflect. The first one we're looking at is reflection. So when a wave encounters a boundary between two mediums, some of the wave will always be returned to the original medium. The wave will reflect back from this boundary according to this rule. So this here, there's no real big trick to knowing. You can think about it logically, but it's also something you might read and focus in. More rigid medium, then the reflected wave will come back on the opposite side. So here we have a pretty narrow rope or almost a piece of string, and it's going into a much more rigid, more solid piece of rope. So as it's moving, you're going to have some of the wave continue on, and that wave is going to cause it to wave going in the same direction. What we call this is the transmitted wave. This is the transmitted wave. It's going to go and hit a fixed point, inverted or reflected. So this wave is now on the other side, going down. Alright, this is called a reflected wave. Or, in this case, it is inverted. So as it comes back, it's going to go from the thicker medium into the thinner medium. When it's going into the thinner medium, it's going to keep that reflected wave on the bottom, coming back. And it's going to still be inverted. So the reflected wave, then reflected wave will come back on the opposite side, or again, the term we use is inverted. Inverted. If we have the opposite, if the wave reaches a less rigid medium, then the reflected wave will come back on the same side. So here we have like a slinky or a really soft spring. So when the wave is moving, coming towards the less rigid rope, its transmitted wave is still going to be up. It's still going to be on the top there. So that's the transmitted wave. However, the reflected wave in the slinky, as it went from something that was more rigid to less rigid, it's going to come back and be reflected up again. Or the reflected wave in that slinky is going to be upright. So now that we've looked at how wave can bounce back or it can be reflected, we need to now look at how it can be diffracted. What it means when it's diffracted, it means that the wave bends around a corner and fills the space behind an obstacle. So if we have a wall here and we got a little slit in it or a little space in between, if we have something with a smaller wavelength, that wave is going to be coming straight for that slit. As it hits it, what happens is the light is diffracted, or the wave is diffracted. In other words, it starts to squeeze through this little slit, and then it's going to bend around to start filling the spot in these directions. the white light or the wave is going to come through. If we have something with a larger wavelength, we're going to see something similar but a little different. So if it has a larger wavelength, that means that the space in between the waves is going to be bigger than the space was above. Because these are bigger, wavelength, it's going to diffract. The window, it can light up the whole room. It doesn't just light up a beam that goes straight through. That beam may be more bright, but it still ends up lighting up the whole room. What happens when we have two windows or a double slit is a little bit different. We're still going to have our waves coming towards, but now they're squeezing through two spaces. And each of these spaces, you're going to see the same thing happen. You're going to have the wave bending around those slits in space. But that's going to end up happening on both of them. You're going to have your light here as well, or your waves are going to bend here. So now you get your waves here as well. And that overlapping we call interference. So when you have a double slit, the waves diffract, which means that they bend around the slit to light up the whole space and time, and they also interfere. So we'll talk more about what interference is, but let's make a few more notes here on diffraction. So once a wave is constant, so once a wave has started, its frequency remains constant. That means if you're solving a problem using the universal wave equation, which again is velocity is equal to wavelength times frequency, if it gives you the frequency at the source and you're solving for the velocity later on, you can still use that same frequency. It's the same the whole way. The speed is different though. The speed depends on the medium. Speed depends only on the medium. In other words, what the wave is going through is going to determine your speed. If you're in a more dense medium, that means you're going to, if you're in a more dense medium, that means you're going to be moving faster. If you're in a less dense medium, you're going to be moving slower. Alright, a fat or a more dense medium is going to increase your velocity. A less dense medium is going to decrease your velocity. Same frequency. Your speed is going through, so whether you're going through air or water or oil or whatever else. And your wavelength, your forces are going to change in that as well. The last bit of terminology we're going to look at when we're talking about waves is interference. So interference occurs as the result of diffraction, or it's when waves meet and superimpose on each other, creating a momentary new wave with a new amplitude or displacement. So this gives us something we call the principle of superposition. The displacement of the combined sounds like a lot, and that is pretty heavy terminology. But to simplify it a little bit, if we look back on the last page when we were looking at this double slit experiment, or this double slit, where they're overlapping here, that is what we call the interference. So this line here going through where they overlap, that's your interference. Remember, your diffraction means that your waves are going to go out the medium, but where they overlap, that's your interference. So we can have two types of interference. Your constructive interference means that they're in phase. Or if you have two waves that are going in the same, they have the same, let's say crest in this case, when they overlap, they're actually going to add together and make an even bigger wave. They're going to superimpose on each other or superposition on each other. As they pass through, they work together. When they work against each other, you're going to have destructive interference. So in this case, we have one crest that is up and then we have one trough below. As they meet each other, they're going to balance each other out into equilibrium if they are. And that means that once they move through, the waves are going to continue on. So again, if we look back at constructive, let's call this our first amplitude 1, and we're going to have amplitude 2. As those two move together, again here you would have amplitude 1 and amplitude 2. And when they overlap, you're going to have twice the amplitude, or you're going to have amplitude 1 plus amplitude 2. You get the sum of them together until they pass, and now they go back to being their original and own amplitudes. Same when we have destructive. But now we have one, we can think of this as a positive direction or an amplitude 1 going up. And we can think of this as amplitude 2, but in the negative direction. If they are the same, when they hit each other, they're going to balance out. So at this point, you have canceling each other out. And then, again, they continue on through